Our next speaker is Saraswathi Subramanian from University of Arizona, who will be talking to us about ultraviolet coronagraphs for Habitable Worlds Observatory. And then you'll want to stand over here.
Yep. Okay. Can everyone hear me? Yes. Okay, thank you. Okay, I'm Saraswathi. I'm a postdoc at the University of Arizona, and I'm going to be presenting our work on UV coronagraph designs for the Habitable Worlds Observatory. Okay. As Chris started up really nicely this morning, with the Habitable Worlds Observatory, we want to look at biomarkers at a variety of wavelengths, and we also want to have starlight suppression of the order of 10 billion times. So I'm going to be focusing on the UV end of the spectrum. So the broadband absorption of ozone is a good indicator of life because it is often used as a proxy, since you can even observe the signal in weakly oxygenated atmospheres. The idea is, can we have a potential NUV coronagraph for the Habitable Worlds Observatory? We don't really hear a lot about high contrast imaging in the UV because it is very challenging. You have tighter requirements on wavefront sensing and control, you have stricter tolerances on coating, and you're a lot more susceptible to the effects of contamination. You also have lower flux because of the reduced system throughput in the UV, and also intrinsically less bright sources. So this is not just a problem at the focal plane, but you also have fewer photons to do wavefront sensing and control. And to add to all of this, the contrast also scales as wavelength, and it goes as lambda to the -4 because of surface error effects, and lambda to the -2 because of the DM effects. So all of this is very pessimistic, but there are some assumptions that go into getting these contrast scaling laws. So here you have a plot when you actually consider more realistic PSTs and with a non-uniform DM actuated response, which is close to reality. And these are derived assuming a 6.5 meter telescope with a 96 by 96 DM, which is sort of what we're baselining for HWO. Another thing to keep in mind is that since we're going towards shorter wavelengths, we can actually have a larger inner working angle. So if you look at the unshaded region in the middle, which is from 9 to 48 lambda over D, which is what we would have for like a UV coronagraph, then the contrast ratios when you go from UV to the visible, it's only a few times, which means UV coronagraph is probably not that difficult. So we're taking a few steps to push us towards demonstrating UV HCI at UFA, and the first of that is a design study of different NUV coronagraph architectures, and that's what the rest of my talk is going to be on. We're also working on developing analytical tools to understand the design traits that go into this. We also have a grad student working on performing the metrology of key optical components, and I'll share some of their results towards the end of the talk. And our final goal is to have NUV demonstration on SCOOB. So SCOOB is our vacuum-compatible testbed, and we are using a charge 6 vortex with a 1K DM, and we get to contrast of about 2 times 10 to the -9 in narrowband in vacuum. So coming to the design study, so we started with these 3 telescope pupil geometries, the ESC1, 2, and the LUV pupil, which is just the ESC1 with like more segments. I also want to mention that there are other groups that are working on UV coronagraph design studies as well, and they're considering apodized pupils, VVCs, shaped pupils, and so on. So the first coronagraph we considered was the VVC, simply because of the legacy we have with SCOOB. So we're using the same charge 6 vortex for the focal plane mask, a 90% Leo stop. And the question we asked was, so we know we can have a larger inner working angle, and we know we want to increase the throughput in the UV, so can we just have a simple coronagraph and sort of exploit all of this? So we're considering a classic Leo coronagraph, which has just a circular occulter at the focal plane mask, and a phase apodized pupil Leo coronagraph, where we have a knife edge focal plane mask, and the apodization comes from the DM itself. So we're starting with some Fraunhofer modeling using POPI, and because we're going only from like the pupil to the image planes, we are considering only a single actuator DM at this point. Sorry, a single DM, 96 by 96 actuators at this point, so we have a one-sided dark hole. Our wavefront sensing and control is done using electric field conjugation, and we're taking all 3 coronagraph architectures with the 3 telescope pupils, so we have 9 combinations in total, and we're we're estimating the core throughput that we get, the contrast in a one-sided dark hole at 300 nanometers in monochromatic and 10% bandwidths, and also how sensitive these architectures are to global wavefront error and also segment misalignments, and how it changes when you go from hexagonal to keystone segments. So starting with throughput, so each plot here is with a different telescope pupil, and we can see that the VVC has the least throughput, and this is because you lose 50% of your light just from the polarization filtering. And it's interesting to note that we actually have more aggressive Leo stops for the CLC and the PAPLC, but still independent of your telescope pupil, your throughput is higher compared to the VVC. And then when you start looking at the contrast, so the images here are all what the dark holes would look like at 10% bandwidth. So all of them hit like the 10 to the minus 10 that we would expect for habitable worlds. But the CLC and the VVC are an order of magnitude better. And in this particular case, the CLC actually even outperforms the VVC, if you see. And then going from AAC1, which is hexagonal, to keystone segments, we see the same trend actually continue, where all of them hit 10 to the minus 10, and CLC and VVC are still an order of magnitude better than the PAPLC. When we go to the lower B pupil, the contrast degrades because you have more segments, so that's sort of expected. And I do want to mention here that this is not like the best contrast. We can still iterate a few design parameters, and we can probably still hit similar contrast to what we got in the other two cases. So in terms of contrast, all of them have comparable performances. And then going to the global wavefront error, so we introduced them in the form of like the lower order Zernickes. I am only showing the Zernicke mode that each architecture was most sensitive to here. And on the left, it's how the contrast degrades in the full dark hole region, like going from 7 to 15 lambda over D. And on the right is how it degrades at the edge of the inner working angle, which in this case is like 7 to 8 lambda over D. And if you have the 10 to the minus 10 as your like threshold, the VVC starts to hit that threshold at like a few tens of picometers of few tens of picometers of wavefront error, whereas the CLC and PAPLC are a lot more resistant, and you need like a few hundreds of picometers of wavefront error for it to degrade beyond the 10 to the minus 10 levels. And this is for EAC1. So when we go from this to AAC2, so going from hexagonal to keystone, the trend still continues where VVC is still the most sensitive, but then if you, this is closer to like the hundreds of picometers wavefront error. So if you look at just the VVC, and in terms of being sensitive to global wavefront error, then it's better with a keystone compared to hexagonal segments. And then similarly, if we look at how sensitive they are to segment misalignment errors in terms of like piston, tip, and tilt. So here it's with the AAC1 pupil, and each plot is for a different architecture. The solid curves are how the contrast degrades within the full dark hole, and the dashed curves are how they would degrade at the edge of the inner working angle. Here it's interesting to see that independent of the architecture, they all start to sort of hit that threshold at about the same level of the segment wavefront error. And then again, going from AAC1 to 2, we see that again, within AAC2, all the three coronagraph architectures start to degrade performance at similar segment wavefront errors. But going from AAC1 to 2, the keystone, the coronagraphs are a lot more resistant to segment errors as well. So to sort of like quickly summarize all of that, when we look at throughput, the simpler coronagraph designs outperform the VVC because even with like more aggressive Leo stops. In terms of broadband contrast, the CLC and VVC have comparable performances, and the CLC sometimes outperforms the VVC. While the PAPLC had the least contrast, or like I guess the highest contrast, it still hit the 10 to the minus 10 that we expect for habitable worlds. But at the same time, the PAPLC was also the most resistant to global wavefront errors. And CLC was like somewhere intermediate for a given pupil, and the VVC always had the highest. And in terms of segment, piston, tip, and tilt errors, all three architectures had comparable performances with a given telescope pupil. So the sort of one-line summary of all of this is that we can consider simpler coronagraph architectures for UV so that we can exploit the fact that we have a larger inner working angle to increase our throughput. And as I mentioned earlier, so Kat is one of our grad students, and they're working on component-level metrology of the optics that go into our coronagraphs, and they're using an atomic force microscope to do this. And this will feed into our contrast budget, and that will help improve our modeling efforts. We are also working on developing end-to-end models of some of the architectures that I just showed so that we can better understand what our contrast would look like. And the final goal would be demonstration on scope with a VVC and an SPC. Thank you.
Great talk. I had a couple of questions. Since you're only looking from 7 lambda over d out, how come you don't go to a higher than 6 charge vortex to improve your sensitivity to lower order wavefront errors?
Yeah, that's good. So we just took the scope model and started off there, but we can in the future look at higher charge vortex.
I think a charge 8 or a 10 would really
help improve.
Yeah.
Yes.
And the other thing was a scalar vortex. Asking for my own personal reasons, but would definitely improve the throughput, and we can explore the sensitivities there too.
Any other questions? I have a question.
Yes.
Of all of the things that you presented, what keeps you up the most at night in terms of doing UV coronography on Habitable Worlds Observatory?
I think just all of it. I don't think I can pick one. Yeah.
That's fair.
Yeah.
All right. Well, thank you so much.